They're in physics.
Okay, let's jump in. How about this? What if the very things we take for granted, space and time, aren't as fundamental as we think?
Right.
What if they actually emerged from something even deeper? Something like, say, the interconnectedness of quantum systems, or what physicists call quantum entanglement.
Exactly. That's the kind of mind-bending question that SQS grapples with, and it's really where our exploration begins. The entire SQS framework is built upon three key foundational principles.
Three pillars. Yeah.
The first one is quantum holography. Now, you've probably encountered holograms before, right? Maybe on a credit card or something.
Sure, yeah. Looks 3D, but it's flat.
Precisely. Quantum holography proposes something kind of analogous for the entire universe. The idea is that all the information contained within the vastness of the universe is actually encoded on its boundary, like a cosmic DVD, holding all the data needed to reconstruct the 3D reality we experience.
Wow. So all the galaxies, all the stars, even us, all that information is somehow written on this, like, cosmic screen. That's a bit hard to picture.
It is, but here's where it gets really interesting. There's a key equation here. What this tells us is that the entanglement entropy, which is basically a measure of how much quantum systems are intertwined or linked together, is proportional to the area of that boundary.
Okay.
And crucially, this quantum interconnectedness, this entanglement, is what actually gives rise to the geometry of space-time itself. While this idea was initially inspired by black holes, SQS extends it to the flat and expanding universe we actually observe.
So the more entangled things are on this boundary, the more space and time we get inside. It's almost like the universe is built on relationships. That really makes you rethink what's fundamental.
It really does. It suggests that information isn't just something in the universe. It might be the very stuff the universe is made of.
Okay. What's the second principle?
The second core principle of SQS is symmetric gauge invariance.
Gauge invariance. Okay, that sounds a bit technical. What does it mean in this context for the universe?
Yeah, think of symmetry in physics as representing things that stay the same, even when you change how you look at them, your perspective. Symmetric gauge invariance in SQS proposes that all the fundamental forces we know, electromagnetism, the nuclear forces, strong and weak, and even gravity.
Even gravity?
Yes, even gravity aren't separate things, but are actually different faces, different manifestations of a single fundamental symmetry. It's described by this mathematical group called ToE.
The single symmetry for everything.
Pretty much. And here's the real kicker. Space-time itself is also part of this fundamental symmetry.
Wait, hang on. Space-time is part of the symmetry, along with the forces. How does that work? That's a big shift.
It is a big shift. So within SQS, the mathematical description of space-time, what we call the metric, and the math describing the other forces, the gauge fields, they're actually unified. They become parts of a single mathematical object. Let's call it math-cal-mu. This elegant unification suggests this deep underlying interconnectedness at the most basic level of reality. It potentially offers a simpler way to understand how everything interacts. So instead of forces acting on space-time, it's all sort of woven together from the start, governed by this one symmetry that's, well, surprisingly simple at its core, beautiful even. It has an elegance to it, yes.
Okay, what's the third foundational principle then?
The third is entanglement-driven dynamics, or EDD. Now, this principle offers a really new way to think about how the universe changes and evolves over time.
Correct.
Instead of the traditional quantum physics approach, which involves summing up all possible histories, a system could take the path integral.
Right, Feynman's idea.
Exactly. SQS proposes that the universe's evolution isn't about summing possibilities, but is driven by a continuous process of maximizing its overall entanglement entropy across its whole vast network of quantum systems.
So hold on, the universe isn't just passively existing, it's actively trying to become more interconnected. How does that drive the actual physics we see?
Well, in this EDD framework, the path integral is effectively replaced by this principle of entanglement maximization. Mathematically, you might see it written as math-cal, but the key is that the action is basically proportional to the entanglement entropy. There's a fundamental constant involved, lambda.
Okay.
So think of it like this. The universe's goal, if you like, is to increase its interconnectedness. And this fundamental drive is what shapes the flow of time and the evolution of everything within it. It's definitely a mind-bending concept, the idea of the universe actively organizing itself through entanglement.
Okay, that is mind-bending. So, recapping. We've got the universe as a quantum hologram, all forces in space-time unified under one symmetry, and the whole thing evolving to maximize entanglement. What are some of the big, maybe unexpected implications of putting these pieces together?
Right, this is where it gets really interesting. One of the most fascinating implications is how SQS treats what we call the dark sector, dark matter and dark energy.
Ah, the big mysteries.
Exactly. SQS suggests they aren't separate mysterious things we need to find, but rather they emerge as inherent aspects of the fabric of space-time itself.
So wait, the stuff making up, what, 95% of the universe might not be some exotic particle after all?
That's the proposal. SQS suggests that dark matter arises as a kind of residual flux of entanglement. Think of it like ripples or stresses in regions of space-time that aren't directly connected, almost like a background quantum foam of interconnectedness.
Quantum foam.
And the density of this dark matter is actually related mathematically to how the entanglement entropy changes across space, its gradient.
So it's a structural property, not a substance.
Precisely. It's a significant departure from the standard model's search for new particles. Instead of adding new ingredients, SQS suggests the missing mass might just be a feature of spacetime's own complex structure and could be a simpler, more elegant explanation.
That is elegant, if it works. What about dark energy, then? The thing speeding up the expansion.
SQS proposes that dark energy is related to the gradient of the entanglement entropy of empty space itself. Essentially, it's the energy associated with the inherent interconnectedness of the vacuum.
The energy of nothingness being connected?
Sort of, yeah. The formula from our notes, lambda frac 1 frac right, it shows that the cosmological constant, lambda, which represents dark energy, could actually change over time as the universe's overall entanglement evolves. So the idea is compelling. These huge, dominant, yet mysterious parts of the cosmos might not be fundamental stuff, but rather fundamental aspects of spacetime's entangled structure.
That's a really neat way to potentially tie together some of the biggest puzzles in cosmology. What other surprising predictions does SQS make?
Well, it also delves right down into the realm where quantum mechanics meets gravity, the incredibly tiny Planck scale. SQS predicts that at these minuscule distances, spacetime itself becomes sort of granular and non-commutative.
Non-commutative. Okay, that sounds mathematical again. What does that imply for, like, actual reality down there?
Essentially, it means the order in which you measure things, like position coordinates, actually matters. It's like if you try to define a location by going left then forward, you might end up in a slightly different spot than if you went forward then left. Usually, order doesn't matter, but here it might.
Oh, weird.
Yeah. Mathematically, it's described by something like x2, where the tiny Planck length. The key thing is, this isn't just math. It might be testable.
How? How could we possibly test something happening at the Planck scale?
One potential way is by looking at very energetic events, like gamma-ray bursts traveling across billions of light years. If spacetime is grainy or non-commutative, high-energy photons might travel slightly differently than low-energy ones from the same burst.
Ah, so they'd arrive at slightly different times.
Exactly, a phenomenon called spectral lag. And interestingly, the Fermi LHT Space Telescope has observed some tentative hints of this kind of effect. It's not definitive yet, but it's a potential avenue for testing SQS.
So watching the most powerful explosions might tell us about the very texture of reality. That's amazing. What about bigger structures, like how dark matter clumps around galaxies?
Right. SQS seems to offer a natural explanation for the observed shapes of these dark matter halos. Many observations suggest these halos have a chord structure, meaning the dark matter density is sort of flat in the very center.
Rather than spiking up sharply.
Yes, rather than the sharply peaked, cuspy profiles that some other dark matter models predict. SQS, because it links dark matter density to the gradient of entanglement entropy, naturally seems to produce these flatter cores.
That's interesting because that core cusp problem has been a persistent headache for standard cold dark matter models.
It has, yeah. So SQS potentially resolving that is quite appealing. And then there's the early universe. You know, the James Webb Space Telescope, JWST, has been finding these surprisingly massive galaxies really early on.
Right, they seem too big too soon.
Exactly. That's a bit tricky to explain in the standard picture without some fine-tuning. SQS suggests that in the very early universe, you could have had these dense hubs of dark matter entanglement forming very quickly.
Like seeds.
Like seeds, yes. These entanglement hubs could have acted as gravitational anchors, accelerating the formation of those massive galaxies much faster than expected, potentially without needing special initial conditions.
So these early entanglement hotspots basically gave gravity a head start.